Hi everyone, today we'll be discussing the LeetCode problem of the day, trapping rainwater 2. In this problem, you're given a 2D grid of height map representing height of each unit in the 2D matrix. And you just have to return the volume of the water it can trap after raining for several years. So if you see the first example, we have the grid like this, and this is the height map. So the first row, the height is 1, the next height is 4, then it is 3, then it is 1, then 3, then 2. So the middle row, we have height 3, this has a height 2 before the water is being filled, height 1, height 3, 2, and then height 4. And finally the third row, height 2, 3, 3, 2, 3, and 1. So in this height map, if we fill the water, then we just need to return at the end how much water will be stored. So one thing we can see that in the boundaries, the water is never filled. So we just need to check in between how much water is filled. So for this input, we just need to check for these values on these cells, how much water is filled. So if you see on this, the water filled will be up to 3. So the total water is 1. Height 3 minus this height 2. Water filled on this cell will be 1. If you see on this cell, the height is up to 3, but the grid height is 1. So total water on this cell will be 2. And in this cell, we can't fill any water because it will overflow from this side or that side. And finally, on this part also, we can fill the water till height 3. And since this height is already 2, so 3 minus 1, it is 1. So the total, we have 4 units of water that is filled. Now if we see the second example, since again we can't fill the water in any boundaries, we'll just check in between. So in this, it will be filled up to height 3, and it already had a height 2. So total, we can fill 1 unit of water here. So I think it will be the same thing for all these. So we have 8 units of water, and in the center, we can fill 2 because the height is 1. So 3 minus 1 will be 2. So 8 plus 2, total we can fill 10 units of water. Now let's go over the approach. So one thing we have established is we can't fill water on the boundaries. So we just need to check all the values in between, how much water we can fill on each cell, and we just need to add all of them up. Suppose we are checking how much water we can fill on this cell. So that means on this cell. So for this, we need to know the boundaries of this cell. So we can see this is a boundary, and this is a boundary, and this, and this. So for this particular cell, we have some boundary, and the maximum value this cell can hold is equal to the minimum value of the boundary. So in this case, the minimum value of the boundary is 3. So this cell can hold only 3 units of water. And since its height is already 2, the total water it can hold is 3 minus 2 equal to 1. So to know the amount of water for each cell, all we need to know is the minimum value of the boundary. So suppose we have a random element, and it has some boundary. Boundary can be in any shape, and these boundaries have multiple values. So this boundary value is 7, this is 9, and this is 6, this is again 8, and this is 3, and this is 4. So suppose this is the boundary of this cell, and the cell value is 1. So the maximum water this can hold will be equal to the least value of the boundary, which is 3. So we can only fill up to 3, and since its height is already 1, so 3 minus 1, we can fill only 2 units of water. and suppose if the cell value itself is 5. So if the cell value itself is greater than or equal to the least boundary, then we can't fill any water here. Suppose if we see in this example, its boundary is this, and this. So one of the boundaries is 2. So its boundary is less than its height, so we can't fill any water on this. So all we need to know is, for each cell, find least boundary height for each cell. So this is the key to solve this problem. All we need to know is the least boundary for each cell. So if we just see the example again, okay, for this 2, the boundary is all this, and the least boundary is 3. So 3 minus 2, we can have 1 filled here. Now again, we'll see for the next element. For this one, again the boundary is same, so the value will be 3 minus 1, which is 2. And finally, for this, the boundary is like this, and in this the least value is 3. So the answer is, the value it can hold is 3 minus 2, which is 1. So total we have 4. So similarly we can see for this as well. For each of these elements, the boundary is 3. So we can similarly calculate the value. I also like to take another example. Let me just write it quickly. 3, 3, 3, 4, 4, 4. Yeah, suppose we have this example. In this we have all these boundaries, and we can fill water in only these parts. So if we look at this, the boundary is like this. So in the boundary, we can see we have a 3. So the boundary value is also equal to its value. So no matter what water we fill, it will flow out through this way, because the boundary value is less than or equal to the height of this element. So if we fill any water here, it will flow in this way. So similarly, if we fill any water here, it will flow through this way and again flow. So for this example, the total amount of water that it can hold will be 0. So like we discussed, we just need to find the least boundary height for each cell. So the best way to do that is, first store all the boundaries in a priority queue, minimum priority queue, and from that, just when you pop the element, you will get the least value of the priority queue. So you'll get the least boundary. So from that boundary, you can just iterate on the neighbors. So suppose you have a boundary. This is the least boundary because you just popped it from the priority queue, and this will have 4 neighbors. So just check if all the neighbors, if any of the neighbors is not visited, and just visit it and just check the value. So suppose this boundary has a value of 4. If its neighbor has a value of 1, that means this cell has a least boundary 4. So the value it can hold is 4 minus 1 equal to 3. So this value can hold 3 units of water. And once we are processing a neighbor and we are able to fill some water, we should also add this in our priority queue. So this will become a new boundary. And while adding it, since we are filling the water up to level 4, the new height should be 4 and not the 1. And suppose we find an element of its boundary which is greater than itself. So this value is 6 and its least boundary is 4. That means we can't fill any water here. So we simply add this in our priority queue. And whenever we visit any cell, we mark it as true so that we don't repeat it again. And at the end, we just keep checking for all the values, and when the priority queue is empty, that means we have covered all the values, and whatever is the answer, we just return it. Now let's quickly code it. So first we'll create a class which will store the cell, because we are adding it in a priority queue. So we have a class cell. It will have like 3 parameters. One is height, and one is row, and other is column. Let's just initialize it. Call height equal to height. Yeah, the class is created. So let's first get the row size and column size. N equal to height map dot length, and m equal to height map of 0 dot length. And now let's also create a priority queue. And the type will be cell, new priority queue, and we will use a custom comparator. Okay. So in the priority queue, we want the least elements to be appeared on top. So we'll just return based on the height. Return integer dot compare a dot height and b dot height. So whichever has the least height, it will be given more priority. So the priority queue is done. Let's also take answer variable. And now we just need to first iterate on the boundaries and just add it in the priority queue. So first let's iterate on the row. So in the row pq.add, okay, we need to create a new object. So in this row, we are adding the first element, and we'll similarly add the last element. This is the first element of the row, and the last element will be m-1. Similarly, let's do it for the columns as well. Also, when we add it in the priority queue, we also need to mark the visited as true. So let's take a Boolean array. And yeah, so initially it's all false. So when we add it, we will set it to true. I m-1 equal to true. So the same thing, we'll do it for each columns. But in the columns, we'll only add the first and the last element because we're only interested in the boundaries. So this will be flipped 0i, and this will be m-1, n-1, I, n-1, I, and this will be 0 and I, and this will be n-1, I. So now we have added all the boundaries, and let's just iterate on the priority queue. While pq dot, so while the priority queue is not empty, cell pq dot remove. So this is where we get our first boundary, and from this boundary, first we need to iterate on all these neighbors. So each cell has 4 neighbors: top, bottom, left, and right. So for the boundaries, let me just create a direction array, so it will be easy to iterate. Equal to, so we'll add all the directions. So if you want to go to the right, so the row remains same, the column should be increased by 1. And if you want to go to the left, row is 0, column -1. If you want to go to the top, then row is -1, column is 0. And if you want to go to the bottom, row is 1, column is 0. So now we can just iterate on this direction array. I equal to 0, I less than 4. X will be cell.row plus directions of I 0. Similarly, we can have y cell.column plus directions of I and 1. So once we get x and y, this value can also go out of this grid. So suppose if we have the boundary as 3, and if we try to go to the top, it will go out of bound. So the first thing is we need to check if the boundary, if the x and y are really inside the grid or not. So we'll just use a check function, and if it's inside the grid, we just need to check if it's not visited. And let me quickly fill the check function as well. Public boolean check. We have x and y, and then the boundaries n and m. So we can just return x should be greater than or equal to 0 and y greater than or equal to 0, and x is less than the row length and y is less than the column. So once it is checked and it is not visited, so that means we have visited this x row and y column from the least boundary. So all we need to check is if the height of this x and y is less than the boundary or not. So where is the height map? Yeah. So the height of x and y, if it is less than our cell dot height, HEIGHT, if it's less than the cell dot height, then we can definitely it will definitely store some rainwater, and that will be exactly equal to cell dot height minus height map of x and y. So in this case, we have the boundary 3 and the cell value as 2. So the amount of water it can hold is 3 minus 2, 1. And once we have filled the water, we need to add it in the priority queue, x and y. But here the height will be the cell height, which is the new height. And else means the height is greater than the cell height. Suppose for this one, the boundary is 2 and the cell height is 3. So in this case, we can't fill any water. So we just add this in our priority queue, and the value will be the original value itself, height of x and y. So we don't do any changes. And once we have added it, we need to mark the element as true so that we won't process it again. And yeah, that's it. And at the end, we can just return our answer. Delete this and let me submit. Yeah, and it works. Finally, let's do the time and space complexity analysis. So coming to the time complexity, first we are creating a priority queue, and in the priority queue we are just adding the boundaries. But eventually we are adding all of the elements. So in the priority queue, we will add a total of n into m elements. And in the priority queue, the operations, the remove and add operations will be of time log n. So the total complexity will be n into m log n into m. And the space complexity will be just order of n into m, because we are just creating a directions array of n into m, sorry, not directions, the visited array of n into m. And also this priority queue will contain the total n into m elements. So time complexity is n into m log n into m, and space complexity is order of n into m. Since n and m are very small, so this will pass. I also have the code in Python. If anyone wants to view it, I'll add it in the description as well. And let's catch up in the next video.